All right, you guys might hear a little bit of background noise for the intro, but then I will go on mute. Welcome, everyone. Today we have the pleasure of welcoming Dr. Maria Walach as our speaker today. You guys might hear a little bit of background noise for the intro, but then I will go on mute the YouTube, apologies. Maria received her PhD from the University of Leicester, where she studied the modes of magnetotale response, including substorms, steady magnetospheric convection, and Sawtooth Events to varying solar wind driving using global auroral images. Following her PhD, Maria moved to the University of Lancaster, where she began studying the ionospheric response to magnetospheric input using the superdarn radars. As part of this current work, Maria is developing the time-varying electric field model, an ionospheric electric field model, which takes into account the time-varying nature of the solar wind and other phenomena such as substorms and geomagnetic storms. Today, I'm delighted to have Maria discuss ionospheric convection and the auroral responses to solar wind driving and the time-varying conditions and night-side events to these responses. So with that, Maria, thank you for presenting, and you can take it away.
Thank you, Kyle, and thank you for the introduction. Hi, everyone. It's a pleasure to be here today and to be speaking to you all about this topic. We've already had a really great series of talks, and when Kyle first asked me to give this talk, he told me that he was setting up a series of night side and auroral talks, and he wanted me to talk about the tail modes. So that's what I'm going to do. As he already mentioned, I did my PhD on this, and I've done a little bit of work since then. So what I will be doing is talk a little bit about published results, but then also show you some newer stuff that is a bit experimental and is not published yet. So hopefully there'll be something exciting in there for everyone. And just as a heads up, there is a little bit of a warning here and a caveat. There will be some gaps in my slides because there is a lot of literature, and this is a really vast topic. And so as a result, there will be gaps inevitably, but hopefully it gives you a starting point and something to go from, especially with the series of talks that we've already had. Hopefully there's something new in here and something that hasn't been covered in previous talks. So first up, we're going to start off with a bit of background. So on the left here, I've got this classic sideways view of Earth and the magnetosphere. And when the interplanetary magnetic field is southward, we have this classic Dungy cycle idea going on. So on the left here, we've got a sideways view of the magnetosphere. On the right, we have a top-down view. These are not to scale. They're obviously very, very simplified images of what's going on. But this gives us a framework to start off with. And Dungy came up with this idea that as you have southward IMF coming from the sun, and hitting the Earth's magnetosphere, you can get reconnection here on the day side in this approximate purple region, which means you are adding open flux to the lobe of the magnetosphere, and eventually this reconnects again in the purple region here on the night side. And so this gives you a cycle of plasma convecting through your system. When you look down at the pole, in the northern hemisphere, for example, you might see this where noon is towards the top, and you can see these colored lines show you the plasma flows, which are analogous to these magnetic field lines moving, or the magnetic flux being redistributed, if you will. And so this entire thing is a connected system, which means we can look at different parts of it and different measurements. And this tells us something about what's happening elsewhere as well. And we have to keep that in mind with everything we're doing. And so we have this day side driving on the day side here. So when the IMF is southward, we get reconnection here, and this opens polar cap flux. And then on the night side, reconnection closes it. So that's what we're starting with. And this Dungy idea predicts and explains the convection of plasma. But there was one detail that the Dungy papers, the early papers, did not encompass, and that's the unbalancing of reconnection rates. And this came later. And we can talk about this as the expanding and contracting polar cap paradigm. So this is what happens when you have these reconnection rates on the day and night side not being balanced. So on the left here, I have again 2 convection patterns similar to the previous one, but what's happening here on the top one is we have day side reconnection only. And on the bottom one, we have night side reconnection only. And so if you just have day side reconnection, you're opening flux on the day side. So again, you are convecting plasma into your polar cap here, which is this boundary of open closed field lines. And this means that your boundary is going to expand because you're adding plasma to your polar cap, or magnetic flux, if you will. And so this boundary is going to expand equatorward. And at the same time, you're going to get a return flow on the outside. So that's important to keep in mind, is that one reconnection rate can drive all of these things, but depending on which one of these 2 reconnection rates is dominating, you either get a contraction or an expansion of the polar cap. You can also have it being balanced, which is when the polar cap doesn't change size. So the day side and night side reconnection rates will be balanced in that case. And so this is given by this equation, which is a simplified application of Faraday's law. And there's a great body of work behind all this. This is just very simple diagrams of it, but there have been many papers about this. And here we have an animation showing this in practice. This is from Steve Milan, and I think he might have had something very similar in his talk, so hopefully this will already be familiar. And what you can see in this animation, here we have the polar cap, again, increasing in size as your day side reconnection rate is turned on here, and then we turn on the night side reconnection, and so we start getting closing of polar cap flux here. And for some time here, this is balanced, and now it becomes unbalanced because the night side reconnection is dominating. And so you can see in the ionosphere, you would see the plasma moving around as these dots do. These lines of convection are also equivalent to our electrostatic potential. So we have an electric field going across the polar cap as well at the same time. And so really this idea encompasses a lot of what's going on, a lot of dynamics, and it's a very helpful way to think about when we think about day side driving and what's happening on the night side, and we think about this on a global scale. So in my talk, I'm going to mainly be talking about large scale dynamics. And so this is very helpful context to put everything. So what's happening in the expanding and contracting polar cap and what's happening with the Dungy cycle is a very dynamic process. These reconnection rates aren't always balanced, as some early papers suggested. And so we need to think about the different things going on. So there is a paper by McFerrin et al. From 2008, which talked about the response of the Earth's magnetosphere to changes in the solar wind. And that's really sort of the basis of what, or one of the bases of which I'm going to talk about today. So there's a really good paper. If you're interested in this, I recommend you go look at it. In this paper, there's essentially, it's a list of the sort of responses you can get to solar wind driving and changes in the solar wind. And I've taken them out of the paper and put them in these boxes here. And we've got a really big green box here, which is the geomagnetic activity box. And this really encompasses everything that happens. This obviously is not all encompassing. There are other things happening in the magnetosphere that I've not listed here. But this just gives you a starting point, really. And so we have magnetic storms on the outside here, and I've put them as a separate thing from everything else because they're sort of the largest geomagnetic activity you can get. Geomagnetic storms encompass the entire magnetosphere, and it's really a sign of large-scale system changes. Then we've got some other ones. You might see some familiar ones here in the auroral activity circle or the reconnection activity circle. And really what I wanted to do here is distinguish between things that are primarily driven or accompanied by auroral activity and things that are accompanied by reconnection activity or driven by. And you can see that a lot of them are in the middle here. And that's because a lot of them encompass reconnection and auroral activity. And that's what I wanted to talk about today. And in fact, during my talk, you're going to see this steady magnetospheric convection events. They're going to start moving into the auroral activity box. And we're going to consider some of these in the context of the expanding and contracting polar cap paradigm. Yeah, I think that's everything. So let's consider some of the magnetospheric modes in the context of the expanding and contracting polar cap paradigm. So I'm going to be talking about substorms, steady magnetospheric convection events, Sawtooth events. There'll be a bit about geomagnetic storms in there and recurring substorms. And so these are different types of events and different ways the magnetosphere responds to solar wind driving. And the questions that I'm interested in are, can we see differences in the night side response to responses and the auroral dynamics? And what do these differences tell us about the physics? And so we're going to use various parameters, various measurements for proxies of reconnection activity, and see where we go from there. And so we're going to delve into some data. I'm going to show you some events, and I'm going to show you some conclusions that I've drawn from them. And yeah, so for example, we can use solar wind measurements, and they can be used as a proxy for day-side reconnection. This has been done many times before. There's a great wealth of literature behind this as well. I'm going to be using the parameter from Milan et al. To do this, but essentially what we're talking about is a southward interplanetary magnetic field. And when it's primarily southward, you get reconnection on the day side. And we can calculate what that reconnection rate might be from the solar wind measurements, and then infer what's happening as a result. And so substorms, this is a very small slide given the size of the topic. You might have heard of these before, but they are events that happen in the magnetosphere, and they happen due to solar wind driving. So they can be identified in different ways, and we have different precursors to substorms. So one of the things that is very iconic to substorms is that we have a growth, an expansion, and a recovery phase. There might also be some smaller things happening in there. So for example, in the aurora, we can see these auroral beads forming here. This is from an auroral camera, and this is from a study by Calmoni et al. From 2018. And you can see these brightenings. They start off with these auroral beads and then grow. And that's really a precursor to a substorm about to be happening. And we're going to be talking about on a very large scale. So at the scale that I'm going to be talking about, these sort of beads don't really come into it. But the growth, expansion, and recovery becomes very important. And here I'm showing an animation that I've made where you can see the auroral brightening happening, which is the onset of the substorm. So the start of the expansion phase, essentially. That would be here, the onset at 0 minutes. When this animation runs to that time, again, you will see a brightening here that then expands. And so during the growth phase, what we see is the auroral oval expand. So it goes to lower latitudes, and this is because we have a growth phase where day-side reconnection is active. It enhances the polar cap flux, so your polar cap grows in size. And then as the expansion phase starts, night-side reconnection starts, which starts to eventually decrease the size of the polar cap again. And that's exactly what you see in this animation here. And I made this animation using data from the image satellite. This is a satellite that went over the polar cap and took pictures essentially of the aurora. And there were two cameras or two instruments that can measure the auroral intensity. There's one taking pictures of the proton aurora, and which is the spectrographic imager. And then there's also the wideband imaging camera, which took essentially pictures of the electron aurora. And we can combine these to make these sort of average images timed to substorm onset, and that's what I've done here. And so I'll be showing more of that data and more of these averages from that data throughout my talk. On the right here, I've got a picture taken from an old paper by Ujima and Nagata, and this is from magnetometers on the ground. So this is AL and AU index, and AL and AU are essentially magnetometer indices. So this is measured on the ground, and this measures the electric current. It's a proxy for the electric current in the ionosphere due to this reconnection and the plasma moving in the ionosphere. And you can see this great enhancement here, which is how early studies of the substorms were being done. And we'll see more about that in the future. So AL and AU measure they're a proxy of this, of the flows in the ionosphere, which is due to this reconnection cycle. And so I'm going to contrast substorms with steady magnetospheric convection events. Substorms by themselves have already been studied in great detail, but I think what's interesting is when we start contrasting them with different types of events, because that's when we can then draw conclusions of how similar different events are. So first I'm going to be talking about steady magnetospheric convection events, and as the name already says, this is when convection is steady. So you want day and night side reconnection rates to be balanced. And we cannot solely select here by steady solar wind conditions. So we need to look for further indicators of the system's response. And we can use the overall indices for this. I've already mentioned AL and AU. AE is a combination of the two. And this has already been done. So I've taken an event list by Kissinger et al. And adapted it for my use. But we have to be careful with this event selection, because there is a seasonal dependence to this, which was shown by McWilliams et al. In 2008. So we're going to take this into account, and I'm going to show you how that can be done. So here I have an example steady magnetospheric convection event as identified by Kissinger et al. So you can see here is a bay of AU and AL. So they're both enhanced beyond some threshold here that is marked by the dashed line. And the idea here really is that they stay enhanced for some time and fairly steady. On the top here, I'm showing the polar cap flux in black. And this is from the image data. So this is from the auroral. So, and it's measuring the inner boundary of the auroral using an oval. And with that, you can calculate how much magnetic field essentially is encompassed with this in this area, and that's what the polar cap flux is. And so then we have the auroral radius here as well. And here we have the auroral brightness from the Wick instrument on board image. So this is the electron emission of the aurora. And on the bottom, I'm showing BZ and phi D. Phi D is the day side reconnection rate calculated from solar wind parameters. And so you can see these orange lines here, they are two substorms that have been identified by someone else. And you can see they're accompanied by these brightenings. And that's not what we want during a steady magnetospheric convection event to be happening. If we want to sort of investigate what happens during a steady magnetospheric convection event and a substorm, and we want to look at these separately, the best thing to do is to make sure one's not happening during the other. And so I went through this event list from 2000 to 2005 when we have image data, and I deselected all the ones where we have substorms happening. The substorm list, by the way, comes from the image data. So that's the Frey et al. List that I used for this. So there's a manual selection going on, and that yields much better results than using one that just uses AL and AU. Here's an example of a good event, one that was selected, and you can see the polar cap flux indeed does stay fairly steady. We don't have any substorms happening, and we've got some driving happening here as well of the magnetosphere. So there's day side reconnection going on, and AL and AU are enhanced during this time. So we can look at how what happens during these events. And here I have a superposed epoch analysis of this. On the top left, I'm showing AL and AU again. And this is the brightness from the auroral emission. This is the IMFBZ, so the southward component of the interplanetary magnetic field. And then on the bottom, I have the polar cap flux. So we can look at these events individually, or we can superimpose them and look at this on average. So that's what a superposed epoch analysis is, where you basically line up the time zero, so the onset time, and you look at what's happening statistically. So what I've plotted here is the mean and the standard error on the mean. That's the shaded region. And I checked the median too, if it's of interest, and they are very similar. So we have several thousands of events for the substorms, and we have around thousands for the steady magnetospheric convection events. And then, so the black line just shows you the average for the entire data set. And so let's compare the two. So you see for the substorms, we have this bay here, and that's similar to what Ajima and Nagata had in the very early paper. And we see this brightening of the aurora, which has been shown many times before. So this abrupt and very extreme brightening during the substorm onset. And we have the IMFBZ indeed being southward prior to onset, which loads our polar cap flux and gives us this growth phase where the polar cap increases in size. And then a slow and steady northward, sort of not northward turning, but becomes less southward after onset. And then here we have the polar cap flux. Again, this increases in size. So this is our growth phase. And then we see there is some time after onset where it doesn't seem to change. And that's when your night side reconnection has kicked in, but not overtaken the day side reconnection. And eventually, H indeed shrinks in size, which is when your night side reconnection takes over. Now in blue, I have the steady magnetospheric convection events with preceding substorms. And so this is where I changed the timing of the steady magnetospheric convection event to match preceding substorms. Steady magnetospheric convection events are known to have substorms starting with them. And that's what we see here really. You can see the blue and the red curves are very, very similar. But then you keep driving the system, which leads to a slightly different response. So you can see, for example, the IMFBZ continues to stay southward, and your polar cap flux as a result doesn't decrease by as much and continues to stay enhanced. So the steady magnetospheric convection event typically starts around here, and then this continues for some time. Similarly, the the auroral brightness stays slightly more enhanced. And there were also some steady magnetospheric convection events that I found without preceding substorms. And these are these green ones. There are a lot less of them than for the blue ones. And the reason is that typically they do start with a substorm, but for these green ones, they might have been events where we couldn't identify a substorm beforehand. So there might have been a similar sort of initiation happening, but we did not directly see it. And what's the interesting thing about this is that you're essentially driving the system in a very similar way, but then you continue to drive it and you get a slightly different outcome. So when we have very prolonged driving, this leads to these steady magnetospheric convection events. And just on the top here, I've got these events again, but on a very much longer time scale. And so we're looking 20 hours before to 20 hours afterwards here. And you can see that these green ones that didn't have a preceding substorm, they did have a lot of activity beforehand. There was a lot of driving beforehand, and for many of them, it was for several hours beforehand. So there's some preconditioning of the system happening here. And there was a study by Milan et al. In 2019, which looked at this from a slightly different angle. They looked at substorms with no recurring substorm. with no recurring substorms for at least 6 hours, but then looked at for continued solar wind driving. So the different colors here show substorms with different amount of length of solar wind driving after the onset. So you can see this here for these purple ones. The solar wind stopped, the driving stopped after just 30 minutes. And then as we're going in color, the solar wind driving continues. And so if you're just selecting the substorms like this, you get something very similar to the SMCs with preceding substorms. And the longer you drive it for, the longer your activity continues. This SML and SMU, by the way, is very similar to AL and AU that I showed earlier. And this is the expansion of a parameter. This is a parameter similar to the polar cap, but it's measured from the Ampere data set. So this shows us that the whole idea here is very consistent. And just to put it in context again with what I showed earlier, for this very short period here, we've got this prolonged driving here, and this is really what's driving things. And so this prolonged, steady-ish driving leads to SMCs. And we can look at what the Auroral looks like as well due to this prolonged driving. So prolonged driving indeed leads to prolonged auroral activity. Here I'm showing superposed epoch analysis of the Auroral data, and this is different MLT bins. So we're averaging over different local time hours. So if you take your Auroral oval and you're slicing it, and you take the average across those, and then sort of look at it in time. So time is on the x-axis here. That's what we're seeing here. And these are color-coded by the brightening at onset. So, a green increase shows a brightening relative to onset, and purple shows a decrease. And we can calculate this auroral brightening by MLT sector, and that's what you're seeing here. So this is for the substorms in red at the bottom here, and the top one is SMCs with preceding substorms. And for both of them, you can see that our onset is near 23 MLT, and then this brightening moves east and westwards, and we continue to have a very bright auroral oval, especially in the early hours of the morning. For both the SMCs and the substorms. SI12 and WIC, again, are the two different cameras on board the image satellite, and they give us slightly different wave bands of the ultraviolet aurora. Another thing we found that I've not shown here actually is that the brightening starts at higher latitudes for the SMCs and then moves to lower latitudes. These carry on for some time, these brightenings. And that really suggests that a stable reconnection site establishes itself further down the tail than where the substorm begins. So that's another interesting thing about these. So we have this prolonged driving creating prolonged activity, but what if we ramp up the intensity? So we see this brightening here, and it continues for some time. It continues for the SMCs, but what if we ramp up the intensity of the solar wind? What if we have stronger solar wind driving? And that's what we can look at as well by selecting our events differently. So if the IMF is really, really strong, we get a different type of event called a Sawtooth event. We also get geomagnetic storms, actually. So there's different types of event you can get if your solar wind driving is strong and prolonged. One of them is a geomagnetic storm. So this can encompass types of events within it. So a geomagnetic storm really is where the ring current around the Earth is enhanced, but you can also get auroral phenomena within that or other types of events. Then the Sawtooth events, they are like quasi-periodic global particle flux variations. That's how they're often measured or identified. And they present themselves as recurring low latitude substorms with short-lived auroral brightenings. And hopefully by the end of this talk, you'll be convinced by this. as a result of this sort of dual mode, they're being identified one way, but they also show as something else in a different data set. People often misidentify them as substorms. And that's because this is what substorms look like if you look at the aurora on average, and this is what sawtooth events look like if you look at them in the aurora on average. You can already see this. We're 40 minutes before onset here, and you can already see the aurora is much brighter for the sawtooth events. But then at onset, we see a similar brightening, but it's much more extreme. It moves to lower latitudes. It encompasses many more hours of MLT. And so we already see some differences here, and we'll dig into that a bit more. But first, let's talk about how they're identified. So they were first identified, I think, in 1995. This is this paper that everyone refers to, and you can see these are from 3 different spacecraft at different local times, and they were all measuring these same changes in the proton flux at geosynchronous orbit. So geosynchronous orbit is generally quite far in comparison to where our sort of convection maps to, our high latitude convection that I talked about earlier. But nevertheless, we see these very strong changes in the particle flux data. And so these quasi-periodic changes are what are referred to as sawtooth events. We also sometimes get similar signatures during substorms. And for the substorms, really, the idea is that you might get one of these when you have your reconnection happening and particle flux is being injected into the inner magnetosphere. But during a sawtooth event, really, this happens on a much more global scale. So these spacecraft are separated by several hours of local time. And that's really characteristic for a sawtooth event. That and the fact that they are these quasi-periodic oscillations. So they look really interesting, and we're going to see what that looks like in comparison to substorms in terms of the ECPC, so the expanding and contracting polar cap paradigm. So the sawtooth events that I'm going to be using are identified from particle flux data observations at geosynchronous orbit. They're from some papers with published events lists, and we have around 273 events for these. I already mentioned that they look similar to substorms, so that's a bit of a spoiler there, but as a result of that, we had to make sure there were no substorms happening at the same time, similar to the SNCs earlier, and so that reduces the list to this number. I already mentioned we have many substorms, and really the idea here is that the sawtooth events are, there are several ones of them in a series, and they are separated by 3 hours of magnetic local time, and you measure them with more than one satellite, really. And so the other thing is that they're dispersionless, which means that you see these drops in your particle flux data at different channels all at the same time. And yeah, so we're going to compare those, and we're going to compare them again using this data from the image satellite, with which we can measure the polar cap flux again, and we can look at the auroral brightenings. So this is shown here. Again, I've got the same sort of parameters that I had earlier for the steady magnetospheric convection events, and I've sort of left on the very faint lines of them so you can see a comparison. And we've just added on the sawtooth events here in orange. And hopefully what you will notice immediately is that they look very similar to substorms, but there's an offset, which means that they're happening at different energy levels. So AU and AL are clearly enhanced here. The IMFBZ is enhanced, so we're driving the system here at a much higher level. So I did mention earlier what happens if the system is being driven at steady and enhanced southward IMF, and that's what's happening here. And then the polar cap flux increases similarly to substorms, but it's much higher values. So What that means is you have a larger polar cap, and you're opening much more flux as well as closing more flux. So there's a higher convection going on there. And then as a result of all this, our auroral brightness increases to higher levels as well. So here I have again this superposed epoch analysis, again showing it separately from the SMCs, and I've added the solar wind speed here, the day-side reconnection rate proxy, and the SimH as well, because they're quite interesting. You can see SimH is clearly offset, so these tend to happen when we have geomagnetic activity definitely happening at lower latitudes, which is unsurprising since these are measured at geosynchronous orbit. The day-side reconnection rate, by the way, is this, which I think is my only equation in the entire talk. As I said, it's a proxy for day-side reconnection measured from the solar wind. There are other things you could use, and I think you would get very similar results. So our polar cap flux is much higher, but what we do see is that for these sawtooth events, similar to substorms, we have a growth, expansion, and recovery phase. So that's interesting. They're essentially looking very similar. And we already saw this in this animation that I had earlier, but just to show them side by side here, we've got this, for the sawtooth events, the aurora is already bright prior to onset, but when onset happens at 0 minutes, we will see this brightening at 23 MLT, which is down here. In all these clips, by the way, we're looking down at the pole and noon is towards the top. And you see this brightening, and then the brightest parts of the protein aurora expands and it shifts duskward. And this is really quite abrupt. The sawtooth events are also brighter, but the onset brightening fades much quicker, which we'll see again on the next few slides. And the auroral oval is much more enlarged for the sawtooth events. So yeah, this is very obvious when we look at the radial bins. So again, we can sort of take this auroral oval and we can take averages across the MLT slices, but we can also take radial slices. And I've taken radial slices going from this inner circle here to this outer circle to take averages of the auroral oval. And this is what is shown here. On the top two show the substorms again, and the bottom two show the sawtooth events. So in each panel, the top is towards the auroral pole, magnetic pole, and the bottom is towards the mid-latitudes. And you can see this expansion and contraction of the polar cap here happening for both the substorms and the sawtooth events, but it's much more extreme for the sawtooth events. We can look at the MLT bins again in the same way we did for the SMCs, and you see that the brightening for the sawtooth events down here dims very quickly. Whilst the auroral oval was much brighter to begin with, the dimming is much more extreme. So then what I wanted to think about is, can we see an expansion and contraction of the polar cap in the convection data, as well as we saw for the auroral data? And really, to keep in mind for this, we need to think about really that we're looking at a connected system. So if our auroral oval brightens and expands, then our convection has to move as well. And this is a diagram I've taken from Steve Milan's paper. I think he talked about this in his talk, but really we do have to keep in mind that it's a connected system. So if we think our auroral oval expands, our convection pattern has to expand as well. And so I thought I would look at this and see if we can see this. And to do this, we're going to use SuperDARN data. So SuperDARN is a network of ground-based radar systems, and we have these convection measurements of the ionosphere from this. It was purpose-built to do this, so we have many, many years of data. But what you'll note from this animation was that before 2005, really, these orange radars at lower latitudes didn't exist. So I'd give it a go anyway, but what we have to keep in mind here is that our data essentially is restricted in the Northern Hemisphere to this sort of circle. And so what I wanted to ask is, do we see the corresponding changes that we see in the auroral oval in the ionospheric electric field? So there have been a number of studies that tried to do this before. And the two main ones that I want to draw attention to are these two. And they both looked at these auroral substorms and looking at superdown data with them. And they saw the very clear things that we expect, so a growth and expansion phase, and then a recovery as well. And this study in particular looked at substorms happening at different latitudes, and they saw very different signatures. So I thought that was very interesting. And I thought, can we extend this and look at sawtooth events and see the same thing? Now, these are animations that I made with substorm data and sawtooth data. So these are the same event lists that I had earlier. And what you'll see here is you can see the data from the superposed epoch analysis from superdown. The colors show you the flow vector speed of the ionosphere, and the white lines show you the electrostatic potential. And we see immediately that the convection pattern is more twisted for the substorms, especially near onset. But we don't see the same amount of expansion and contraction as we did in the auroral data. And I was a bit puzzled by this, but then I realized that other people also found this. So for example, the Grocott study also showed this. And we see this for the sawtooth events and the substorm events. We do see a convection slowing on the night side here near onset, which could be convection breaking due to the enhanced aurora. And that's something that I think is an open question still. I think this was alluded to in many studies previously, but hasn't really been answered fully. And so the convection is much stronger for sawtooth events and extends to slightly lower latitudes than the substorms, but we don't see the same amount of expansion and contraction as we did earlier. And this is because we have an observation bias which restricts our pattern. So as I mentioned earlier, between 2000 and 2005, we are limited to this sort of area here, which means we're not going to be measuring the full extent of the expansion and contraction. So I thought, can we look at this from a different angle? And I think we can. We just have to keep in mind that there's bias in every data selection that we do, whether that be human, automatic algorithm, or machine learning. And so in my case here, it's the data selection. And that's the main problem. And so I thought maybe we can choose our events in a different way and still come to similar conclusions. Hopefully that is the case. So I spent a bit of time looking at geomagnetic storms. I identified these using an automatic algorithm. Because of time, I'm not going to go into too much detail here, but what I'm going to say is I used SimH to identify the geomagnetic storms, and then I used superdown data to look at the size of the convection pattern, essentially. And so there are two parameters that I extracted. One is this flow reversal boundary, which is analogous to the open closed field line boundary, or should be at least. And then this Hepner-Maynard boundary, sorry, which is where the flows go to zero at the lower latitudes. And so we can look at this statistically. And during a geomagnetic storm, we have the main phase where the SimH enhances very abruptly, the recovery phase afterwards, and the initial phase beforehand. Sorry. One of the things that became very apparent was that this Hepner-Maynard boundary and this flow reversal boundary, they are correlated, but this correlation changes. Sorry, as you have different amounts of geomagnetic activity. Really sorry. So I thought, can we look at this from an even different perspective? And rather than looking at sawtooth events, can we look at substorms versus recurring substorms? And do we get something similar to what we got with the sawtooth events? And so I picked out substorms, compound substorms and isolated substorms from Colin Forsyth's SOFI algorithm event list, and this uses the supermap indices. And so we can split this data into substorms where it tells us when a growth phase is, an onset and a recovery phase. This is shown here. This is the SME index, which is an auroral index measured by ground-based magnetometers. And so we have this growth, onset, and recovery phase. In purple here, I'm showing the isolated substorms, and then the dashed lines show the upper and lower quartiles. And then in blue, we have the first compound substorm, which has a very similar trace. And then we go into the second compound substorms. Because they're a series of substorms, they then don't have their own growth phase. They just go straight into the onset from the recovery. And you see this in red. And then we have the third compound substorms where SME is even higher, and then anything bigger than third I've grouped together up here. And so I also do a data quality selection with SuperDown. So this means we don't have unlimited amounts of events, but there's still more than hundreds, which allows us to do a superposed epoch analysis like this one. And we can look at the dataset driving again, the cross-polar cap potential from SuperDown, and this return flow width. So this is the difference between the Heppner-Maynard boundary and the flow reversal boundary here. And I wanted to see, first of all, do they all start off on an enlarged oval, the compound ones that is, and how do they compare to the isolated substorms? Do they change drastically over time? So I'm going to show you a series of these. First of all, comparing these two. The dataset driving continues for the first compound substorm after onset. You can see this here, which means that our cross-polar cap potential, though it's very similar, stays enhanced, and especially at the end here, gets a little kick. And our return flow width behaves very similar to the cross-polar cap potential. So it stays similar to the isolated substorms, but then gets a little kick at the end. And this becomes important because when we move to the second compound substorms, this is what the blue ones essentially go into afterwards. They start off enhanced because they got that little kick beforehand. So we've preconditioned our system here, and our second compound starts essentially much higher values already than our isolated substorm. And this is what alongside this continued driving, is what allows the system then to go into a series of substorms essentially. And we see this when we go into the third compound, sorry, which behaves the same as the second compound, but the onset starts off at even higher levels. And this means that the system is unable to reach equilibrium levels before we reach the end of the recovery phase. Okay, so our day side reconnection continues here. Our night side reconnection continues as well. And we're just continuing to drive the system, but it's not given enough time to recover, really. And so when we go into the even higher numbers of series in our compound series, we see that this climbs even higher. So if I go back, you can really, if I loop through it, you can really see this climb. And yeah, for this parameter here is our return flow width, and this is lower here than it is for geomagnetic storm main phase, which I thought was interesting. But it is comparable to the recovery phase, which is when we get most of our substorms during a geomagnetic storm. I'm really sorry about the coughing. I'm at the end now. So if you're going to take anything away from my talk, I wanted to be that prolonged driving does not always lead to prolonged brightening of the aurora, but we do get some interesting events, and it's important to think about how you're choosing your events when you're looking at them, because depending on how you pick them, you can get either very similar results in one data set, but different ones in another. So remember that the Sawtooth events, although they look the same as the substorm events in some of the data sets, They look like spiked substorms if you look at auroral data, but keep in mind that if you're measuring data at a geosynchronous orbit, you're getting something very different there. And I'll just leave these other conclusions up here for you to read, but that's just summarizing what we've already said, really. And this is also summarized in a very nice figure from Steve Milan, which tells you that high latitude substorms first have a day side reconnection rate turned on, then you turn night side reconnection rate on, you get this expansion phase. And if you keep driving them, you get steady magnetospheric convection. If you have a low latitude substorm where you're driving the system at much higher values, you might get some convection breaking on the night side and enhanced aurora. And this then leads back to this. And so you get that series of events happening. Thank you. We're at the end now. If you have any questions or comments, please ask or send me an email. Thank you.
Thank you for a wonderful talk, Maria. We do have a few questions if you still have a few minutes. Okay.
Yes,
our first question comes from Eric Lund. It's with regard to slide 23, and I believe conclusion point 3 on your final slide there. You might have touched bases on it briefly on the convection breaking. So Eric asks, do you have an explanation why sawtooth brightenings fade much more quickly than non-sawtooth substorms?
Oh yeah, so that's a really, really interesting one. I think, so the one thing to keep in mind there is that the sawtooth events, they already start off much brighter than the substorm events. So overall, they're over twice as bright, okay? So that's a really important point. So when I say they fade, it's really with respect to the onset time, that they fade back to that quicker, but the aurora itself does stay enhanced for a longer time. So I think the reason why we see that fading happening quicker, which is not correlated with the timing of the day-side driving, is that there's still aurora happening, it's still very bright, but the fading really just corresponds to things are happening very quickly. So your convection is happening very quickly. Presumably you're going to be closing flux very, very quickly at very large quantities at once. And so I think that's what that corresponds to. It's just a very abrupt closing of flux, and that leads to very abrupt bright auroras. I hope that answers it.
Excellent, thanks.
Definitely some more work to be done there.
So our next question comes from Jason Durr. So he's asking, thresholds are often used to categorize events for substorms, thresholds in BZ, or timing between events which demarcate independent substorms. Are these thresholds grounded in physics, or are they chosen by an examination of events we consider in advance to be substorms or the type of mode we're investigating?
Yeah, I mean, that's a really good question, and I think we're almost moving into semantics. You often, I think with event-based studies, you can often spend a long time trying to decide what your event is. I think a lot of this has a lot of heritage in people looking at data and saying, there's something different going on there, let's look at that. And then if you're trying to pick loads of them out, the easiest way to do that is indeed by using thresholds. So I think that's often the case, but by doing that, we have learned that different things happen, different physical things are happening during these times. So for example, the geomagnetic storms is a good idea. It's a good example. You can categorize them, and yes, it's potentially a spectrum of things happening where one sort of, there's maybe no clear category per se, but if you are using a threshold to categorize it, nevertheless, you are going to get different physical things happening at different ends of the spectrum.
Excellent. Thanks, Maria. We have one other question from Chukwuma Nuro. Can you just very briefly describe what SuperDARN is?
Yeah, sorry, I had to gloss over that very quickly. SuperDARN is a network of ground-based radars. They are in the northern and southern hemisphere, and they are, actually, I'll just go back to my slide, which has some more information on this. There we are. So, I've gone too far. Perils of animations. So it's a set of ground-based radar antennas, and it's a high-frequency radar antenna network. They look at ionospheric convection by looking at radio waves and how they are refracted back from the ionosphere. And so by utilizing the Doppler shift, you can essentially work out whether or not the ionosphere is moving away or towards you. And so by having lots of these radars and lots of these measurements, like is shown here, so these are the field of views of each radar. By having many of them, you can build up a picture of what the convection is doing. So these are some examples of ground-based radar antennas. So they're these big arrays of antennas, and they send out radio waves into the ionosphere, and the backscattered signal pulses are being used to measure the line of sight plasma velocity. I think there's already been a seminar on SuperDARN, so I encourage you to go and look at that as well.
Okay. Excellent, thanks, Maria. And Larry has one comment regarding Sawtooth Events. There's the only event where they have been observed under southward IMF. And more generally, they are identified solely as being a few strong substorms that happen to occur about 3 hours apart. So I think that's in regard to Eric Lund's question as well. So that's it. Thank you very much, Maria. Thank you for giving a wonderful talk. Our next seminar will be our second Python tutorial next week. I'll paste the website in the chat before everyone goes. I'll remind everyone to have a quick look at the last tutorial and the so-called homework before you start, and also to have a quick look at installing Python if you plan to attend the tutorials more often. So with that, thank you everyone, and thank you, Maria.
Thank you. Thank you for having me.